It says that significant figures are normally those digits in a measured quantity 41, 40, 41, 42, 43, 44. So the last digit is the uncertain digit. If I remove the 0, the number would change, it would become 628. Now you would say that why are those zeros significant? And in a non-decimal number, the ending zeros are not significant. Okay, which of the following numerical values, all zeros are significant? So let's see. Hi students, welcome to this session here at Infinity Learn by Sri Chaitanya. Today's topic is going to be significant figures. Now this is a comparatively easy topic. There's just a few laws that once you get, you should be able to answer any question. Okay, but the more important thing with regards to significant figures is understanding what significant figures actually mean and why they are called so. So over here, it says that significant figures are normally those digits in a measured quantity which are known reliably or about which confidence in our measurement plus one additional digit that is uncertain. To explain this, let's look at a scale. Okay, say we have a big scale over here, in which there are markings, maybe it's say a 10 meter scale, okay, or maybe a 5 meter scale. This is 1 meter, 2 meters, it's a really long scale. I've scaled it down, 3, 4, and this is 5 meters. Now over here, you see that something, you're measuring the length of something. So when you see the length, you see that it goes up till here. It starts from here, you started from 0, this is 1, 2, 3. So what do you know as what will you write as the meter length? You will write it as 2. Inside it there are more partitions, okay, there are centimeter partitions and millimeter partitions and so on. But right off the bat, when I see it from out far, I know that it's gone past this 2. So I will put 2. Now I will zoom into this part. When I zoom into that part, then over there you will have maybe over here 1 centimeter, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? These are your, maybe it's like going in centimeters. So in 1 meter, there would be 100 divisions of centimeter. So let's say these are, we start at 40 and 41, 42, 43, 44, 45, 46, 47, 48, 49. This is 50. And you see, this is, I've zoomed in over here. Okay, in between this 2 and 3, there are 100 divisions. When I zoom in, I see that the line ends roughly over here. So what do I know? 41, 40, 41, 42, 43, 44. And it is a little bit more than 44. So what do I write here? I write 2.44. Now again, each centimeter is divided into millimeters. The scale has very high precision. So it's divided into millimeters. You again zoom in over here. When you zoom in, you see that you have this 44 centimeter, 45 centimeters. So this is 44 centimeter. This is 45 centimeter, and in between you have the 10 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is the 10th one. And there you see the line ending over here. So how do you count it? You know it's 1 millimeter, 2, 3, 4, 5, 6. Right? You write here 6. Now, why do I call significant figures? So in the significant figure, you know that this is 2 meters. That is fine. This is 44 centimeters. That is fine. But the last digit that you write is an uncertain digit. It's an uncertain digit. Why? Because since I've claimed that as the last digit, I am claiming that the line should have ended at 6. Since it's the last digit, till before the last digit, till 44, I am saying that it has crossed 44. It is more than 44 centimeters. But as soon as I'm ending with the digit, I am claiming that that is what the length is. But you see, that is not what the length is. There is an uncertainty. It could be anywhere between 6 and 7. I could have written it as 6 or I could have written it as 7. So this becomes the uncertain digit. Everything else is certain. That is what is said over here. Significant figures are those digits in a measured quantity which are known reliably or about which we have confidence in our measurement. Those are these 3. 1, 2, 3. We have confidence in that. We are 100% sure it's greater than 2, 100% sure it's greater than 44. Plus one additional digit that is uncertain, that is the 6th digit over here. So the last digit is the uncertain digit because we are not sure whether it's 6 or 7. Whether to call it 6 or whether to call it 7. Because the last digit is no longer telling you that it is greater than that. The last digit is telling you what it is exactly. Okay, so this is the main funda behind significant figures, why it's called significant figures and how you actually bring them about in real measurements. Now, in your real problems, you'll be more commonly given questions where they'll give you a number and they'll tell you find out how many significant figures there are. So let's look at those laws that will help you find that. First law says that all non-zero digits are significant. Expected, because if you have 2, 3, 4, 5, each of these numbers tell you something. The last number is uncertain, but it's still telling you. It's still giving you information. It's not a redundant, it's not an insignificant number. Next, a 0 becomes a significant figure if it appears between two non-zero. This 0 is significant. All non-zero 6 to 8 are significant figures, no doubt about that. This 0 is also significant because this also gives you a value. It's not in the uncertain part. This is also giving you a certain value. It is also significant. If I remove this 0, the number would change. It would become 628. So the 0 is significant. So the number of significant figures here is 4. Next one, leading zeros or the zeros placed to the left of a number are never significant. Now, over here you see in the leading zeros means these 3 zeros, they are not significant. Now you would say that here if I remove the zeros it would become 42. The number is changing. But it would become 42, but the 42 is actually what you need. If you just change the units, maybe this is 0.0042 meters. If you write it in just millimeters, it would become 4.2 millimeters. So these zeros don't matter. Just by changing the unit, you could eliminate them. So any zeros before the number are going to be non-significant. So there are only two significant figures here, 4 and 2. Next up, the terminal or trailing zeros in a number without a decimal point are insignificant. So if there is no decimal point, then these numbers are not significant. Only these are significant. Why? Same reason. I can just change the unit from centimeter if I go to millimeter. You see, I'm adding extra 0. If I would have gone to meter, it would have just been 426. So changing the unit can eliminate them. So they are not significant. In a number, now this is where students get thrown off. In a number with decimal, zeros to the right of the last non-zero are significant. So over here, there are 4 significant digits. All 4, even these zeros are significant. Now you would say that why are those zeros significant? I know 4.600 just means 4.6, but that is incorrect. Because like I explained, significant figures shows you up till which point you have measured. In our first slide, if you go over here, I got it 2.446 because I went till this decimal. I measured till here. This was a significant value. So even in this case, if the reading has been taken 4.600, it means that they have measured till this decimal point and that value has come 0. Otherwise, the reading would have directly been given as 4.6. The fact that they have mentioned 0 means they have measured till that point and it is 0 over there. So those zeros become significant. Mind you, this is only in decimal, not here. Without decimal, the ending zeros are not significant because that could have been brought about by a change in unit. But if there is decimal and there are zeros at the end, then those zeros actually specify that the value there is 0. I have not just put them at my own wish. Okay, so these are significant. Next up, the power of 10 is irrelevant to the determination of significant figures, which means like this 2.3 meter could be represented as 2.30 10 to the power 2 centimeter, 10 to the power 3 millimeter. These don't have any role in the significant figures. This is still going to be 3 significant figures, 2, 3 and 0. See, the last 0 is important because even when I'm writing this in the centimeter form, I'm keeping it as 2.30 because this 0, if it is mentioned in a decimal, at the end 0 tells you have measured till this decimal and the value has come as 0. Next, significant figures are 3 in each measurement. Over here, trailing zeros in a whole number with no decimal shown are not significant. So like we just said, if there are no decimal, trailing zeros are insignificant. Okay. Now, a choice of change of different units does not change the number of significant figures. Like we just saw, from meter to centimeter to millimeter does not change the number of significant figures. The exact numbers appearing in the mathematical formula of various quantities have infinite number of significant figures. So something like pi, we generally set pi at 3.14, but that is because we are rounding it off. But for mathematical figures, they actually go till infinity. Each term is significant, because if you keep on dividing, that 3.14 is 22 by 7. If you are dividing, you keep on generating the numbers. You'll keep on, it's a never-ending series that goes on. You'll keep on generating the numbers. So each of the numbers are significant because you can exactly get them. You're not putting them randomly. Okay. Next, over here we just need to count how many significant figures there are. So let's do that. Over here there are 4 significant figures. Why? All are non-zero. The only confusion comes when there are zeros. If it's non-zero, right off the bat, you know they're significant. You just have to understand which zeros are significant, which are insignificant. Over here, there are 2 significant figures. Why? Because this is a non-decimal number. And in a non-decimal number, the ending zeros are not significant. Okay? If I would have just put a 0.0 here, no, all 3 zeros would have become significant. But if this 0.0 is not there, then these zeros are not significant. Next up, we have 0.00602. This has 3 significant figures. Because this is a decimal with leading zeros. Leading zeros of a decimal are not significant. Trailing zeros of a decimal are significant. So this has 3. Over here 2.50, this has also 3, because this 10 to the power 10 does not play a role. 2.50, this 0 is significant because it's a trailing 0 in a decimal number. Let's look at a few more. What is the number of significant figures in 0.0310 into 10 to the power 3? This plays no role. These 2 are not significant, but this and even this is significant. Why? Because this is the trailing 0 of a decimal number. So there are 3 significant figures in this. This says number of significant figures in this. So right off the bat, you can count off all non-zero. So 1, 2, 3, 4, 5. Again, this plays no role. So that is 5 significant figures. Okay, which of the following numerical values, all zeros are significant? So let's see. First up, over here, this is significant. This 0 is significant because it is in between 2 non-zero numbers. This is obviously significant. This 0 is also significant. Why? Because it's a trailing 0 of a decimal number. But this 0 is not significant because it's the leading 0 of a decimal number. Decimal or non-decimal, it's a leading 0, not significant. So this is not the correct answer. Over here, 2.02, you can tell that this 0 is significant because it's in between 2 non-zero numbers. So this is our correct option. I can even look at this. Over here, this 0 is significant, but this 0 is not significant because it is the trailing 0 of a non-decimal number. Fine. So that's it. That's our discussion of significant figures. Like I said, the rules are pretty simple, just recognizing which zeros are significant and insignificant. But the key is also understanding what I mean by significant figures, because based on that you can apply the logic about whether a number should be significant or not. Then remembering and understanding these laws becomes a lot more logical and you don't have to mug them up. Okay, so thank you so much for watching. I will catch you all in the next session.